Hello students, welcome to EPG Pathshala. I am Dr. Kajal Jindal from University of Delhi. Today we are going to talk on module Operational Amplifiers under the paper Measurements and Instrumentation. So students, let us see what we are going to learn in this module. The block diagram of operational amplifier along with the schematic symbol and equivalent circuit is discussed. Ideal voltage transfer curve of operational amplifier is explained. Operational amplifier configurations are discussed. Closed loop op-amp configuration as non-inverting amplifier and inverting amplifiers are studied. The expressions for gain of the amplifiers is also derived. The working of operational amplifier as voltage follower is explained. The electrical signals produced at the output of most transducers have a low voltage or power level and therefore cannot be transmitted directly over large distances. Thus, instrumentation amplifiers are required to increase the amplitude and supply the power required to drive the output devices. Instrumentation amplifiers are also needed to provide impedance matching and isolation. Amplifiers are also used to process the quantity to be measured, that is, to perform mathematical operations such as addition, subtraction, integration, differentiation, etc. before it is processed. The basic integrated circuit, which is used in the amplification of electronic signal, is the operational amplifier, which will be discussed in the present module. An operational amplifier, which can be abbreviated as op-amp, is a direct coupled high-gain differential amplifier that uses voltage shunt feedback to provide a stabilized voltage gain. It is called as operational as it was used originally to perform the basic mathematical operations such as addition, subtraction, integration, differentiation, etc. And the word amplifier specifies its capability of providing the voltage gain. Nowadays, op-amps are used for a variety of other applications such as AC and DC signal amplification, active filters, oscillators, comparators, regulators, etc. An op-amp can amplify both the DC as well as AC signals in a wide range of frequency varying from few hertz to megahertz. Since an op-amp is a multi-stage amplifier, it consists of basic building blocks as shown in the figure below. We can see in the block diagram of op-amp that it consists of 4 stages in cascade. The first stage is a dual input balanced output, that is, the double-ended differential amplifier. It provides a high voltage gain so that any loss in the consequent stages can be easily compensated. This stage also decides the input resistance of the op-amp. An op-amp in general has a high input resistance. The output of this stage now drives the second stage called an intermediate state, which is also a differential amplifier and is a dual input unbalanced, that is, single-ended output. The DC voltage present at the output of this stage is well above the ground potential and acts as an error voltage in the desired output signal. Such error voltage will result in a shift in the operating point of the following stages and distort the output signal. Therefore, it is essential to use a level shifting stage at the output of intermediate stage to shift the DC level at the output of intermediate stage down to 0 volts with respect to ground. The final stage is a push-pull complementary amplifier output stage. The purpose of this stage is to increase the output voltage swing and the current supplying capability of the amplifier. It also determines the low output resistance, which is one of the characteristics of an ideal op-amp. Let me now introduce the schematic symbol of an op-amp. The schematic symbol of an op-amp, as shown in the figure below, has two differential inputs, V1, which is the non-inverting input, and V2 is the inverting input. The two inputs are represented by the symbols plus and minus respectively, and it has one output. A signal applied to the non-inverting input terminal results in an amplified output in the same phase, whereas a signal applied to the inverting terminal results in an amplified output voltage which is 180 degrees out of phase with the input. If A is the voltage gain of the op-amp, then the differential input voltage is given by Vd is equal to Vin is equal to V1 minus V2. Output voltage V0 is equal to A times Vd, which is equal to A times V1 minus V2. That is, output voltage is directly proportional to the differential input voltage. The voltages V1, V2 and V0 are measured with respect to ground. An op-amp requires bipolar, that is equal and opposite voltages for its operation. IC741 is the general purpose op-amp IC which can be used for a variety of applications such as summing amplifier, integrator, differentiator, etc. The pinout diagram of 741 IC is shown in the figure. It can be seen that the IC is available in 8-pin metal can DIP package. For 741 op-amp IC, the supply voltages should not exceed plus minus 18 volt. The output voltage is limited by the supply voltages. On an average, the maximum output voltage is 2 to 3 volts less than the supply voltage. In addition, there are two pins 1 and 5, in order to do the offset null. We next move on to the equivalent circuit of an op-amp. The equivalent circuit of op-amp is useful in analyzing the basic operating principles of op-amps and in observing the effects of feedback arrangements. In the equivalent circuit of an op-amp, as shown in the figure, A times VID is the equivalent Thevenin voltage source, R0 is the Thevenin equivalent resistance which is looking back into the terminals of op-amp. If A is the large signal voltage gain, then the output voltage V0 is given by V0 is equal to A times VID, which equals A times V1 minus V2. Thus, op-amp actually amplifies the difference in the voltages applied at the two inputs and not the voltages themselves. Polarity of the output voltage depends on the polarity of the differential input voltage. Let us now study the ideal voltage transfer curve. Voltage transfer curve is a curve between the output voltage V0 plotted against the differential input voltage VID, keeping gain A constant. Thus, it is a graphical representation of equation 3 given before. It is known as ideal, as here the output offset voltage is assumed to be 0, whereas in practical op-amps the output voltage is nearly 0. The curve shown in figure reveals that the output voltage increases linearly with the differential input voltage only until it attains the saturation value, after which it becomes constant. The region in which the output voltage increases linearly with differential input voltage is called the linear region. Positive and negative saturation voltages are specified by an output voltage swing rating of the op-amp for given value of supply voltages. So, positive saturation voltage plus V saturated is always less than plus VCC. Similarly, the negative saturation voltage shown in the figure, which is minus V saturated, is less than minus VEE. So, the region which is to the right of the linear region and the next of the linear region and to the left of the linear region is the non-linear saturation region. Please note that this curve is not drawn up to scale, as if it were drawn to scale, the curve would be almost vertical because of the very large value of voltage gain A. An op-amp has two configurations, namely open loop and closed loop configurations. In open loop configuration, op-amp functions as a high gain amplifier in three configurations: differential amplifier, inverting amplifier, and non-inverting amplifier. In all the three open loop configurations, any differential input signal which is slightly greater than 0 drives the output into saturation because of the high voltage gain of op-amp, which is nearly infinite. Thus, when an op-amp is operated in the open loop configuration, the output either goes to positive saturation or negative saturation or switches between the two saturation levels. This limits the use of open loop configuration for linear applications. However, they can be used in nonlinear applications such as square wave generators, etc. The gain of an op-amp can be controlled by introducing a modification in the circuit which involves the use of feedback. That is, output signal is fed back to the input either directly via another network, This is known as closed loop configuration. For most practical applications, op-amp is operated in closed loop configuration. Let us now discuss about the closed loop op-amp configurations. An op-amp that uses a feedback is called feedback amplifier or closed loop amplifier. The name closed loop is derived from the fact that the feedback forms a closed loop between input and output. The feedback may be positive or negative. If the signal fed back is of opposite polarity, that is 180-degree out of phase with respect to the input signal, the feedback is called negative feedback. It is also called as degenerative feedback as the voltage is in phase with the input signal. Let us discuss the closed loop op-amp configurations. An op-amp that uses a feedback is called feedback amplifier or closed loop amplifier. The name closed loop is derived from the fact that the feedback forms a closed loop between the input and output. The feedback may be positive or negative. If the signal fed back is of opposite polarity, that is 180-degree out of phase with respect to the input signal, the feedback is called negative feedback. It is also called as degenerative feedback. Whereas, if the voltage is in phase with the input signal, if the feedback voltage is in phase with the input signal, the feedback is called positive feedback or regenerative feedback. Here, the feedback signal increases the input signal. Positive feedback is necessary in oscillator circuits. Negative feedback is used in amplifiers as it stabilizes the gain, increases the bandwidth, increases the input impedance, and decreases the output resistance. Negative feedback also reduces the variation in output of an op-amp due to variations in temperature and supply voltages. Thus, we will be studying about op-amp in negative feedback configuration over here. Negative feedback is of four types: voltage series feedback, voltage shunt feedback, current series feedback, and current shunt feedback. Voltage series feedback and voltage shunt feedback are the most important and widely used configurations in amplifiers, whereas current series feedback and current shunt feedback are seldom used. Voltage series feedback and voltage shunt feedback are known as non-inverting and inverting amplifiers respectively and are discussed in detail as follows. Let us discuss the non-inverting amplifier in detail. The circuit of the non-inverting amplifier with feedback is shown in the figure. As we can see that in this configuration, the feedback circuit is composed of two resistors R1 and RF. The inverting input terminal is grounded through R1 and the output is fed back to the inverting input terminal through the feedback circuit. The circuit is known as non-inverting amplifier because the input signal is applied to the non-inverting terminal of the op-amp. The closed-loop gain can be determined as follows. The closed-loop voltage gain of the op-amp, that is with feedback, will be equal to AF equals V0 by Vin. Now from equation 2, we have V0 is equal to A times V1 minus V2, where A is the open loop gain. So from voltage series amplifier circuit, we have V1 is equal to Vin and V2 is equal to Vf, which is equal to R1 times V0 by R1 plus Rf using the voltage divider rule. Substituting values of V1 and V2 in equation 2, we have V0 is equal to A times within the brackets Vin minus R1 V0 by R1 plus Rf, which gives A times R1 plus Rf into Vin divided by R1 plus Rf plus AR1. Thus, closed loop voltage gain AF is equal to V0 by Vin, which is equal to A times R1 plus Rf divided by R1 plus Rf plus AR1. This is the expression for closed loop voltage gain. Now, as we have already discussed that A is very large, of the order of 10 raised to power 5. So, in the denominator, we can have A times R1 is much greater than R1 plus Rf. That is, we can replace R1 plus Rf plus AR1 approximately by AR1. So, closed loop gain AF will be equal to A times R1 plus Rf divided by AR1, which equals 1 plus Rf by R1. Thus, equation 5 shows that the output voltage is in phase with the input signal since the input is applied to the non-inverting terminal. The magnitude of output voltage, that is the closed loop gain, can be varied by adjusting the values of the two resistors R1 and Rf. Or particularly, it can be inferred that it's the ratio of the two resistors Rf and R1 which determines the gain instead of their absolute values. For example, for designing a non-inverting amplifier of gain 11, we can choose R1 to be 1 kilo ohm and Rf to be 10 kilo ohm. Or alternately, we have a choice of R1 to be 100 ohms and Rf to be 1 kilo ohms. Therefore, it is mainly the ratio which controls the gain of the amplifier. Closed loop gain is also related to the gain of the feedback circuit B, as gain of the feedback circuit B equals Vf by V0, which equals R1 by R1 plus Rf. Now comparing equations 5 and 6, we have the closed loop voltage gain AF equals 1 by B. That is, gain of the feedback circuit is inversely proportional to the closed loop gain of op-amp. Now, the closed loop voltage gain AF can also be expressed in terms of voltage gain A and feedback gain B by dividing numerator and denominator in equation 4 by R1 plus RF. Therefore, AF is equal to A times R1 plus RF divided by R1 plus RF on the whole divided by R1 plus RF by R1 plus RF plus A times R1 by R1 plus RF. So we get AF to be equals to A divided by 1 plus A beta. This is the expression for the gain of an amplifier with negative feedback. Next, we will discuss the operational amplifier as voltage follower. It can be observed from the equation 5 that the lowest closed loop gain that can be obtained from a non-inverting amplifier is 1 because the gain is 1 plus RF by R1. So when the non-inverting amplifier is adjusted for unity gain, it leads to an interesting application of op-amp called as voltage follower. The name is derived from the fact that the output voltage is equal in magnitude and in phase with the input signal. That is, output signal tracks or follows the input signal in magnitude and phase. In order to obtain the voltage follower circuit for unity gain, we can see from equation 5 that RF should be said to be equal to 0, that is, short circuit, and R1 should be infinite, which means open circuit, as shown in the circuit in figure 5. It can be observed from the circuit that V2 is equal to V0 and V1 is equal to Vin, so that V0 is equal to A times V1 minus V2, which equals A times Vin minus V0, or I can say the ratio V0 by Vn is equal to A divided by 1 plus A, which is approximately equal to 1, as A is much greater than 1. Thus, V0 is Vn in a voltage follower and hence is the name given. Along with the unity gain, the circuit provides a high input resistance, that is of the order of few mega ohms, and a low output resistance, which is of the order of milliohms, which makes it ideal for impedance matching. Thus, voltage follower circuit is widely used as a buffer between the two networks and is used to prevent the loading on the preceding stage. We next discuss the inverting amplifier. Inverting amplifier is also known as voltage shunt feedback amplifier. Figure given below shows the circuit of an inverting amplifier using an op-amp. In the circuit, the input is applied to the inverting terminal of the op-amp through resistor R1. The output is fed back to the inverting terminal through a feedback resistor RF, and the non-inverting terminal is grounded. Now, before finding out the closed loop gain of the inverting amplifier, it is essential to introduce the concept of virtual ground. We know that V0 is equal to A times VID. Since A is of the order of 10 raised to power 5 and the output voltage V0 is less than the supply voltage, let us say 15 volts in this case, then the input voltage VID will be equal to V0 by A, which will be equal to 15 divided by 10 raised to power 5 and approximating to 150 microvolts. Thus, the value of VID is very small and can be assumed to be 0. Voltage at the inverting input terminal V2 is equal to the voltage at the non-inverting terminal V1. Since V1 is at ground potential, so V2 is also equal to 0. This implies that there exists a virtual ground at the inputs of op-amp due to VID equals 0, that is, there is no current through the amplifier input to ground, although the input voltage is nearly 0. This concept is useful in the analysis of amplifier circuits using op-amp. We now determine the closed loop gain in the inverting configuration. Applying Kirchhoff's current law at node V2, we have In is equal to If plus Ib. The concept of virtual ground implies that Ib is equal to 0, which means that In is equal to If. Or I can say Vn minus V2 by R1 is equal to V2 minus V0 by Rf. Here In is the input current through resistor R1, If is the current which is flowing through the feedback resistor Rf, and Ib is the current which is flowing into the inverting terminal. Since A times V1 minus V2 is equal to V0 and V1 is equal to 0 volt, therefore V2 is equal to minus V0 by A. Substituting the value of V2 from equation 8, we have AF is equal to V0 by Vn, which equals minus A times Rf by R1 plus Rf plus AR1. The negative sign clearly shows that the output voltage is 180 degree out of phase when the input signal, as the input signal is applied to the inverting input terminal of the op-amp. It is thus called an inverting amplifier. As open loop gain A is very large, which is of the order of 10 raised to power 5, therefore in the denominator A times R1 will be much greater than R1 plus Rf. That is, R1 plus Rf plus AR1 will be approximately equals to AR1. So closed loop gain for an inverting amplifier, AF is equal to minus A times Rf by A times R1, which equals minus Rf upon R1. As for the non-inverting amplifier, closed loop voltage gain or output voltage of an inverting amplifier depends on the values of R1 and Rf, or more specifically on the ratio of Rf and R1. Since the gain of the inverting amplifier can be adjusted to any value, therefore it is one of the highly versatile circuits and is used for performing a number of applications. So students, let us now summarize what we have learned in this module. The block diagram of operational amplifier along with its equivalent circuit has been discussed in detail. Ideal voltage transfer curve of operational amplifier has been explained. Operational amplifier configurations were discussed. Closed loop op-amp configurations as non-inverting amplifier and inverting amplifiers were stated. The expressions for the gain of amplifier was also derived. Finally, the working of operational amplifier as voltage follower was explained. Thank you students for your attention.